Black screen, yeah, okay. No.
Oh, interesting.
Change source.
I don't think you'll be able to.
Connect my device. Do you have a?
No, because the HDMI runs into here, so you can't do anything about that.
Is secure? Why would it be?
It's locked from the back, so.
Oh, I see.
Yeah, this is not like an input, it's an output.
Okay.
So you won't be able to.
Anyone has? Okay. Do any of you have a have a laptop with this connector, VGA connector, with MATLAB?
I do.
With MATLAB?
Yeah.
Okay.
Well, actually, wait. I don't think I have that connected.
Okay. Just leave it. That's fine. I'm going to.
Yeah, it's definitely.
I will.
I mean,
It's kind of surprising. There is no HDMI cable here.
for the home drive?
Yeah. Give it to me. Okay, I guess in the interest of time, I'm going to stop using innovative stuff and just use plain old Blackboard. This has a probability of working 100%. So, all right. So we want to design a lead compensator using frequency response approach for a very simple system. So my system is G of S equals to K over S square. Okay, so that's my system. I put it in a feedback loop, unity feedback. And the transfer function T of S is Ys over Rs, S square plus, no, K over S square plus K. So this is a marginally stable system. It has two poles at plus minus j square root of k. So we want to make it more stable. We want to increase the stability margin for this feedback system. And so here are the design requirements. So first, the phase margin must be greater than or equal to 45 degrees. Oh no, that's not the requirement. The requirement is settling time less than or equals to 4 seconds and zeta damping coefficient greater than or equal to 0.45. These are the two design requirements. Okay. In order to get zeta greater than or equal to 0.45, we need the phase margin. So this implies that phase margin must be equal to zeta over zeta 100 multiplied by zeta, which is 45 degrees. So we want the phase margin to be greater than or equal to 45 degrees, because that's phase margin is equal to 100 zeta. So let me put greater than equal to 45 degrees. Okay, and Ts less than equal to 4 seconds requires the dominant pole. So we require the dominant pole to have zeta omega n greater than equal to 1. Okay. So now let's look at the Bode plot of G of S. So Bode G, it's a double integrator. So you have a plot which just goes down. So this is minus 40 dB per decade. And the phase is constant at minus 180 degrees. That's the Bode plot. So what's the phase margin here? Of the original system? So the phase is 180 degrees, right? So the phase margin is equal to 0 degree. You can have a positive phase margin only if the phase angle stays above 180 degree. In this case, because it doesn't go above 180 degrees, the phase margin is equal to 0 degrees. Even if the phase was above 180 degrees, we have to look at where this magnitude crosses the 0 dB line in order to compute the phase margin. So it's exactly minus 180, so phase margin is 0. If it was above 180, then the phase margin would be positive. Okay. So we need to add a phase margin of greater than equal to 45 degrees in this particular problem. So the goal is to design, we cannot do it using a simple gain controller because a simple gain controller is only going to move this curve up and down, and that is not going to change the phase characteristics of the system at all. So we cannot really use a simple gain controller, so we have to use a lead controller because lead changes the phase characteristics. So we need to use a lead compensator to add phase margin. Okay. Now remember from our discussion yesterday, a lead compensator has the following characteristic. This is the Bode plot of a lead compensator, and this is the phase plot of a lead compensator. Magnitude phase of GC, and this is 0 degree. So we need to add a 0 and we need to add a pole to in the controller. Okay. So let's look at the lead compensator design handout. And what does it say? Evaluate the uncompensated system's phase margin when error constants are satisfied. We don't have any error constant. Phase margin is 0. Then the second step in the frequency response approach is allowing for a small amount of safety, determine the necessary additional phase lead phi m. So let's say my phi m is equal to 45 degrees. Evaluate alpha from equation 10.11. Okay. So what is equation 10.11? Sine phi m equals to alpha minus 1 over alpha plus 1. And I want to write down what alpha is. Alpha is P over Z. Okay. So what is phi m and what is alpha? Let's take a look at it. Whoa.
I work for them, so I
Oh, okay.
text them.
All right. I'll change that. Yeah. Thank you very much. Okay, this changes everything. Well, let's continue our discussion. I have to leave around 3:35, so let's continue our discussion and let's see if we need the computer. Okay, so now what is phi m? Phi m is the maximum. Phi m is the maximum angle of GCJ omega. Okay, so the maximum angle is right here. This is my phi m. This occurs, the maximum phase occurs at square root of Zp. So square root of the 0 of the lead compensator multiplied by the pole of the lead compensator. And if you do the math, it turns out that tan of phi m is equal to alpha minus 1 over 2 square root of alpha. Where alpha is P over Z. Okay. Okay. So the goal here is to add a phase margin of 45 degrees because we want the phase margin to be greater than or equal to 45 degrees. So let's be, it says that you have to be conservative and you want to perhaps add phase margin of 50 degrees or something. So you have to add a little bit to the minimum phase angle you want to add to make sure that you don't have any errors in the final solution. But let's assume that 45 degrees is what we want. So we want our phi m, which is the maximum of the phase angle that the lead compensator should add, should be equal to 45 degrees. And then it turns out that phi m satisfies this relationship where tan of phi m is equal to alpha minus 1 over 2 square root of alpha, which is the same as this expression. So that's written in terms of tan. This is written in terms of sine. So once I know phi m, I can actually compute the value of alpha. So let's do that somewhere. Zero 0.707 How do I find alpha? Okay, 0.707 plus 1 equals to 0.293 alpha. Now instead of using MATLAB, I'm going to use my smartphone. What is it?
5.23.
Let me just check. I get 5.80. Yeah. Okay. So we want our P over Z to be equal to roughly 5.8. We can increase it a little bit. We can make it 6. So this is a monotonic relationship. If you increase alpha, your phi m increases. If you reduce alpha, your phi m decreases. If you plot the chart, that's what it's going to look like. So we want our phase margin to be greater than or equal to 45 degrees. So if you want to make an approximation for alpha, you should always bump it up, not bump it down. Okay. So we can go from 5.8 to 6 because we can change phi m from 45 degrees to say 48 degrees or 49 degrees, but we can't really reduce it from 5.8. Okay. So we want the ratio of P and Z to be roughly equal to 5.8 plus. Okay. Anything greater than 5.8. What is unknown so far? What is it that we haven't yet figured out? Yeah. Sorry, what?
The other specification.
So TS, let's get to it in a bit. We first, well, yeah, so that's, yeah, so this is something we haven't yet figured out. So we want our omega n. So let's say we are picking our zeta to be 0.45. Then our omega n should be 1 over zeta. This is roughly 2.2 radians per second. Okay. Now remember that this would imply that our k should be omega n square. And these are all approximations, by the way. So I'm not trying to do anything which is, okay, I should perhaps put approximations everywhere because these are all approximations. This is the first iteration. We might have to do second or third iterations if things don't work out. This is our first iteration. We want our k to be equal to omega n square. The k is right here. Anyone remembers why? So remember, in the second order system, we have the closed loop transfer function is so this is what the second order transfer function looks like. So we know that this has to be greater than or equal to 1, and this is the same as the numerator k. Okay, so that's this value k here. So we want k to be equal to omega n square. We are picking our zeta to be equal to 0.45, so zeta needs to be greater than 0.45. Let's pick zeta to be 0.45. Settling time should be less than equal to 4 seconds, which means zeta omega n has to be greater than equal to 1. So let's pick omega n to be roughly 2.2 radians per second, which would imply that our k has to be equal to omega n square, which is, what is k? Five, roughly 5. I think square root of 5 is 2.236, so this is roughly 5. Okay. Okay. Now we need to plot the Bode plot of this k, which we have found out to be equal to 5. So let's change it to 5. And we need to plot the Bode plot of this specific transfer function 5 over s square. Where do I do it? So let me write it down. Yeah, I have written down the alpha. Zero dB, and this is Bode of 5 over s square. Okay. If I add a lead compensator, how is it going to change the phase characteristics of the system, and how is it going to change the magnitude characteristics of the system? So if we add a lag compensator, let's say here is where I place my z, this is where I would place my poles, somewhere in this region. So this is just approximate region where I'll be placing my 0 and the pole. So until 0, the slope is not going to change because the magnitude slope is 0. I guess everyone is writing, so I'll wait. Okay. Okay, so now let's just listen to me carefully. We want to look at so this is the Bode plot of G. This is the Bode plot of GC, which is the lead compensator. So all the way until 0, my magnitude slope is 0, then it changes to plus 20 dB per decade, and then it changes to 0 dB per decade again. So I'm just looking at the slope. This is where the 0 dB line intersects with the Bode plot intersects the 0 dB line. So the phase margin is characterized by this particular point, the phase at this particular point, and the phase margin is 0. Now the issue is, if we add some phase, if you want to add a phase margin of 45 degrees, it's going to be that maximum phase angle is going to be in this region, okay, because this is the 0 dB line. And the reason why it is a region and not a specific point is because I don't know how the lead compensator is going to change the magnitude plot. So let's try and figure out first, how is the magnitude plot going to change because of the lead compensator. So until 0, let's say this is my hypothetical 0, until 0 there is going to be no change because the slope is 0 dB per decade, and this slope is minus 40 dB per decade because it's a second order system. After this, there is an upslope of 20 dB per decade there, and there is a downslope of minus 40 dB per decade. So my slope is going to be minus 20 dB per decade until I hit the pole. And at pole, The slope is minus 40 dB per decade. And the slope there is 0 dB per decade, so the slope will be minus 40 dB per decade. These two should be parallel lines. Yeah. So this is G multiplied by GC, the Bode plot of G multiplied by GC. Okay. So what's happening to my crossover frequency? So this was my original crossover frequency at which I intersect the 0 dB line. What happened to my new crossover frequency? It's increasing. It's moved towards this side. So this is my new crossover frequency, omega c nu. Okay. And what about the phase characteristic? I just need to add the phase plot of this with the phase plot of GC. So this is my minus 180 degree line. I see that the entire phase plot is above 0 degree. So I'm going to start something like this, reach a maximum somewhere in this region in between pole and 0, and then I go down to 0 degrees. This is my angle of GGC. Okay, there are no colored chalks. Now what's the new phase margin? So this is the new crossover frequency, so this will be my new phase margin. Yes?
So the K you found over here is just from the transfer function, not like the KP of the
No. Yes. So the Kp for the compensator will come if at some later stage. If we need to have a Kp, then we'll put a Kp there. Okay, so the phase margin will come exactly at this particular location. So the phase characteristic of this particular location would determine what the phase margin of the new system is. So we would like this peak to be as close to this point as possible, right? And this peak is going to be at square root of Zp, and this peak is going to be phi m. This is my phi m. Well, minus 180 degree plus phi m, which is the maximum phase of GC j omega. Okay, so now we know that the crossover frequency is going to shift. We are going to add, because of the lead compensator, we are going to add some certain amount of dB here. So it's going to move up, and so therefore my omega c is going to move towards the right. It's going to increase, and that's going to increase my phase margin of the system. So that's exactly what we need to do now. And I'm going to look at the number 4. So we have done all the way to step 3, and we have found alpha to be equal to 5.8 plus. Now we need to evaluate 10 log alpha, which is the midpoint here. This would be 10 log alpha. So I want to write why it would be 10 log alpha. So this